All right, our example code. TensorFlow has excellent support for training RNNs on text data, but and that would be very useful for a lot of you, but that is complex enough that I would like to wait until next week, because we really kind of have to dive into what all of the different text processing code is doing, and I don't want to do that when we're still kind of getting settled on convolutional networks. So I think our finishing discussion of convo nets and our new discussion of LSTMs will be enough for this week, and we can talk about text processing and LSTMs next week. So instead, we're going to train a network to tell the difference between a sync, a sine, and a line. Sync is just another type of function. It looks like this, right? Whereas sine looks like this, and line is just a line. So what I'm going to do is generate a data set of each of these things, and then I'm going to train an RNN to figure out at the end which one it saw. Okay? And notice I'm not going to feed it the entire sequence at once, right? I'm going to feed it in each value one at a time, right? So it'll get this x, then 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 this x. And it's going to have to remember enough of this sequence to figure out the rule at the end. Okay? And I'm going to attempt to make this a little bit difficult because I'm going to give several of these things different periods, right? I'm going to have different frequencies for the sine wave, and I'm going to have different slopes and intercepts for the lines, right? Some will go up, some will go down, some will be kind of nearly flat. Okay. So yeah, these are the run on the entire sequence and then produce one output at the end variant, right? Because it's going to get shown every element one at a time. And then it's going to have to say at the end once that was a sine. So to do this, we're going to use a couple of bits of NumPy we haven't talked about before that are quite useful. One of them is Linspace. Linspace just gives us a list of numbers evenly distributed in an interval, right? So we tell it how many numbers we want, what the starting point is, and what the ending point is, and it gives us an X array of numbers evenly distributed in there. These Linspaces are very good at being the inputs to functions like sine, okay? It's great for being the input of a function, right? So if X is my Linspace, then sine X winds up, or then sine of X winds up with a nice little graph of the sine function over this range. See? So Linspace spits up a bunch of numbers evenly spaced in order between negative pi and pi, right? It spits up 150 numbers evenly broken regularly between negative pi and pi, right? Those are all of the x values in that range, right? So I guess in that sense, it is sort of like a floating point range function, right? That might be a decent way to think of it, is that it's kind of doing what range is doing, but for floating point numbers and with intervals other than 1. Then I can just call sine of that and get me a nice little sine function over that interval. See? Vectorize is how we're going to define our sync function, all right? So if you think, so in p.sine, right, I can call that sine function on one value, right, or an array, or even a matrix, right? And it will intelligently adapt to whatever I give it, right? If it's given one real value, it produces one real value. If you give it an array, it produces an array. If you give it a multidimensional array, like a matrix, it produces a multidimensional array, right? Unfortunately, there is no np.sync function. So we have to write that code ourselves. That could be very irritating, but we have this convenient function, vectorize. Vectorize allows us to give NumPy a function of one variable, right? A function of x, and then NumPy will produce another version that has this nifty property, right? That if you give it one scalar value, it produces one scalar output, but if you give it a NumPy array of values, it produces a NumPy array of outputs of the same shape, right? That makes writing our sync function and using it super easy, right? I can write numpy.vectorize of this lambda expression, and I hope y'all all have seen a numpy or a lambda before, okay? But I have this lambda that computes the sync of one x, right? For one value x, this would produce the sync of that thing. And then I vectorize it, and I get a callable function that has the flexibility of NumPy's sign, right? I can write sync of one thing and get just the sync of that one value, or I can write sync of x, where x is our linspace, and get the whole thing. And we can see that here, right? So the sync function is real easy. It's just that, right? And I vectorized it this way, and I called it on x, right? I used sync of x, and then matplotlibed it the same way that I used sign of x, and matplotlibed it. And here's what sync looks like. Notice that it sort of, I had to go a lot further out. See that? The sign ran, I think it was from -pi to pi. If you want to see the kind of slow dynamics of sync, it takes longer. Like if you want to see it kind of woo and then diminish, you have to look over a wider interval to see it doing that. And so why did I pick sync? Some of you might be wondering, is there some deep reason? There is not. The entire reason I picked sync is because it's easy to write. I mean, for some definition of easy, right? If you know to do this, it's very easy to define. And because it's different from the sign, right? It is different enough from the sign function that the network should be able to learn to tell sync and sign apart, but it's similar enough, right? So it's different enough that it should learn to distinguish them, but it's similar enough that I expect it to be hard, right? That I expect it to have to learn to look for this big sort of bump somewhere right in the middle to learn to do that, right? There's one particular feature it's going to have to learn to seek to tell sync and sign apart reliably. So what is the input shape? In TensorFlow, our inputs have to be sequences, so they should have a shape like this, right? We can omit this none, that is the batch dimension, but we don't have to, right? So omit or not. We need to have sequences, the length of each sequence, and the number of features, right? That is the shape of our input, right? It is a three-dimensional structure, right? Where the first index is the number of sequences, the second index is the length of the sequence, and then the third index is every feature, okay? So, for example, if I had 100 sequences, each of those was 250 steps, and each step had 3 inputs, my input would be of shape none, 100, 250, 3. Okay? If I had 50 samples of 44,100, so, okay, if I had 50 sound samples that were a second long, right? They might each be 44,100 samples in length. That's 1 second at 44.1 kilohertz, right? And they were 2-channel stereo, then my shape would be the optional none, 50, 44100, right? 2 inputs or features in each time step, 44,100 time steps per sequence, 50 sequences or sounds, right? And then this optional none as the batching dimension in case we want to batch train this later. Note that we cannot omit a dimension even if it's 1, right? So if I have a one-dimensional signal, like a single sine wave, I still have to include that last dimension, right? So if I have 100 sine waves, each that have 250 samples per, so 100 sines, 250 samples per sine. Ooh, what the heck? 250 samples per. But then each sample is one value, then my shape ends up being 100, 250, 1. And we can't omit that last one, right? 100, 250, it will not like. We need to do 100, 250, 1. So a good question that you could be asking now is, what do we do if our sequences are different lengths? Well, what you do is you pad them so they're the same length, and then you mask out the padding. This is an ugly and irritating process that we will worry about later. And in the specific case of text, a bunch of the TensorFlow text functions will do that for us automatically, so we don't need to worry about it. All right, so yeah, let's have a video break and then get to our code.